Thank you very much for the kind introduction. It's a pleasure to be here in Finland, providing, I would say, a Canadian perspective on some of the same challenges and opportunities that we have in Canada. And so within Canada, we've had the issues with the pine beetle blight over the early 2000s, and that really ramped up actually forest harvesting over the past couple decades, and now that's actually been declining, and so the forest industries are faced with the same challenge of trying to get more value out of the forests with actually reduced harvesting. And so one of the opportunities that we have actually to create more value is the use of lignin. At least I'm going to try to convince you of that today. And so the lignin actually can also have a big role in terms of helping in terms of our climate impacts. And so I'll talk a little bit about climate emissions related to the material choices that we have. I'll give you a little small bit of wood chemistry in case if you're not familiar with lignin. And then I'll talk about a couple opportunities that there currently are in terms of moving lignin into the market. And then finally, I'll just conclude about some of the really value-added applications that we can use from lignin just by using the functionality that it has from its native state. So this graphic in front of you, we have, when we think about our carbon footprints, a lot of times we think about the energy that we use on a daily basis, and so turning on the lights, our transportation here. But a lot of our carbon footprint actually comes from the material choices. And so this graphic by the Ellen MacArthur Foundation, let's see if my pointer works, here we go. It shows that we have 45% of our potential carbon footprint coming from the materials that we use on a daily basis. And so the graphic on the right side over here, it really highlights the challenges that we have in terms of moving our carbon emissions forward. And so we have about a 500 gigaton carbon budget that we have until the end of the century. Currently, we're moving, if we want to keep at a 1.5 degree C temperature change, we're using somewhere in the range of 40 to 50 gigaton of carbon per year. And so we're going to exhaust this very quickly. And so we need to actually have material choices that can help reduce this. And so one of the material choices perhaps could be lignin. And so this graphic in front of you highlights basically the savings around the carbon footprint that you can have when you use lignin to substitute the material. And so on the y-axis over here, we have basically 100% down to 0% of the savings. And then on the x-axis, we have a variety of different applications lignin's been used in or could be used in to actually reduce that carbon footprint. And so some of this is relatively small in terms of the asphalt savings over here, only a few percentage. But then if we go to kind of the middle of the graphic here, if we're moving into some of the fine or some of the chemicals such as propylene from lignin or adipic acid that can be used to make nylon, we actually can have a significant environmental footprint savings if we do this. And overall, lignin has a relatively move my point over, relatively pretty good carbon footprint in terms of less than a kilogram of carbon equivalent. So you might be thinking, great, lignin sounds like a good story, but some of you might also be thinking, well, what the heck is lignin? And so most of you probably already know this, so I'm preaching to the choir, but if we think about lignin, it's one of the components within the woody cell wall. It's really the cement that holds things together. And so if you have your little microscope to kind of look at the kind of what wood is in terms of the ultrastructure, you come down to this picture and you see all these little white dots. Those are the cellulose microfibrils, and then in between the cellulose microfibrils in this nice cartoon, you have all this cellulose that's encased with lignin. And if you look kind of a little closely at that, you see lignin is this aromatic polymer. And so the pulp and paper industry does a great job of removing the lignin from the cell wall. The problem is that when you begin to remove the lignin, and it's actually pretty difficult to do this, you end up actually changing the structure as you're extracting it out. And so that's one of the challenges, is that lignin separation, you end up actually modifying that structure. And depending upon the methods that you're using, the degree of change can be significant. And so the great thing about the pulp and paper industry, especially the craft process that's been developed, if you look at over here, we have our wood chips. They go through a cook in an alkaline aqueous solution. Lignin is extracted out into the black liquor. That can be concentrated, and then it's sent to the recovery boiler. And so the last presentation mentioned the use of lignin from the recovery boiler. And so we can pull some of that lignin out. And so if we do that, there's a couple processes that have been developed. One's the lignoforce process, one's the ligno-boost process. These have been developed in the really past decade or so, where you use CO2 in order to precipitate the lignin, and then there's different acid washing stages to kind of clean up the lignin. And so this is great. The one issue though, when we talk about lignin, usually people talk about how cheap lignin is, and so it is cheap if you compare it to the heat equivalent value of the lignin, and so that's used to make a significant amount of energy at the mill. But when you begin to do this process of lignin recovery, you need chemicals, you need the actual infrastructure, you need the labor to do that, and so that actually drives the price of lignin up, and so you have to have applications where you can recover that price of lignin recovery. And so this is kind of a busy graphic, but the good thing is that lignin's been actually validated in a number of different applications out there. And so actually trying to make relatively small compounds like your phenolics from lignin, there's been a lot of work around that area. A lot of work in the polymers, and so I'll give some examples today about lignin-based polymers. There's an emerging area of carbon-based materials, and then over the really last decade, and actually a lot of the research from Aalto University itself in terms of making lignin nanoparticles that have extreme functionality. On this right graphic, it's hard to read, but I'll just point out that this is basically the price of euros per ton for lignin applications, and the lignin's color-coded, and so that orange is craft lignin. It ranges from kind of this 250 euros to 900 euros per ton of lignin potential value, depending upon the application there. And so if we talk about lignin, kind of the lowest cost would be the fuel equivalent value. Really the market price for lignin, after talking to a couple of folks in the Canadian forest industries, market price for lignin is really around the substitution of lignin into phenylformaldehyde adhesives. And so lignin has been validated to be used in phenylformaldehyde adhesives. And so that's adhesives typically when you make plywood, and as well as anything like oriented strand board, things such as that. This is great because actually the PF adhesive technology, it uses an aqueous system, it uses a base catalyzed type of catalyst, and so the lignin attributes actually match this in many cases. Epoxy-based systems, the lignin's been used in these systems as well, and so again, if we want to epoxidize lignin, you can actually use aqueous systems with base catalysts, and so that's great because you don't have to dry the lignin. When you get it from the mill, you can just drop it in. If you wanted to use it in polyurethane foams, you usually have to dry the lignin and then mix it into that system, and so that's one issue there. Or you can dry the lignin and then do chemical modification of lignin, and so you can turn lignin into a thermoplastic, and then you can blend it with things like compostable plastics like PLA or PBAT, some of these common plastics out there. The issue there, though, if you don't do chemical modification, if you try to heat process craft lignin, it almost smells like burnt hair. It has this nice garlic smell to it. So there's an issue there. Highlighting one of the kind of newer applications that have been developed for lignin, and so if we don't use craft lignin but use a more native-like lignin, this actually gives you a picture of a piece of plywood that's been bonded together with only lignin, right? And so that's kind of incredible in terms of using lignin directly as an adhesive, and so it's a special biorefinery process that they use to protect the lignin when they isolate it, but then they can just coat it on the wood and they can cure it under heat, and that actually causes the lignin to cross-link together. And so this graphic over here just shows a variety of different lignins being tested, and the green and blue are the kind of the dry strength and the wet strength of the adhesives. And so I think there's a bright future in terms of using lignin for adhesives out there. We have some work in the past where we used laser modification to kind of erode the wood surface, and the remaining lignin could be used in a very similar fashion to the work that you see here. If you don't want to think about biorefinery lignin, if you want to think more about craft lignin, well, you can take black liquor, and there's some nice work from University of Vienna where they made an emulsion of the black liquor, and then they actually reacted the lignin directly in it, epoxidized it, and then they recovered this nice epoxidized lignin powder over here, and then that could be mixed with different types of hardeners and to make this epoxy resin cured material. So that works out pretty great there. We've worked a lot, and there's been a lot of work all around the world with trying to substitute lignin into the polyol component of a polyurethane foam. This actually can work pretty well in terms of relatively large applications. Polyurethanes are wonderful materials because you can go from very flexible type of foam material into a very rigid foam material, and so you can use it for comfort foams to insulation, things such as that. And so that's one possibility for lignin, but the drawback with this is that really there's an upper limit in terms of how much lignin that you can get into the system without lignin itself kind of, I'll say, mucking it up. So transitioning from kind of these kind of foam materials, we can talk about lignin used for carbon-based materials. There's a very bright future for carbon-based materials. And so currently we have carbon fiber that's made from polyacrylonitrile, or PAN. 90% of all carbon fiber is made from this. PAN is really expensive, and so that limits the use of carbon fiber in a lot of applications besides things like the Dreamliner and other types of aeronautic applications. And so if you look around Helsinki, look around Vancouver, there's lots of electric vehicles out there. These have limited range. If we can lightweight these vehicles by replacing some of those materials with low-cost carbon fiber, that's actually a relatively large market. Just a small amount of substitution, we're going to get quickly into the megaton market. And so lignin can actually help out in this area. There's been some recent work, I think, from Purdue University, where they've actually found outstanding properties for lignin-based carbon fibers. And so in this kind of 2 gigapascal strength and 200 gigapascal stiffness. And so these values far exceed things like glass fiber. They're not really to the PAN fiber, but we don't need the properties because we're not going to build airplanes out of this. We want to build car parts out of this. If we look at the carbon footprint here, we have a significant reduction in the carbon footprint for these materials. And so going from 33 kilograms equivalent down to 18 with the substitution of lignin-based carbon fiber. So there's hope there. And then almost my last slide about lignin opportunities. One area is basically exploiting the kind of natural ability of lignin to have these functional materials. Lignin can be a good antioxidant or radical scavenger, seen up here. Lignin also, supposedly lignin first evolved in plants because plants needed sunscreen, and so lignin can actually be a pretty good UV absorber out there. And then lately there's been a lot of work in terms of lignin being assembled into these colloidal particles. And so there's a very bright future there in terms of moving forward. And so really there's a number of opportunities, but it must overcome these challenges. And I think if we actually start thinking about the end product where we want to use lignin and be able to kind of take it from the processes, say if we're using craft lignin, we probably want to use it in a system where we can use a little wet lignin. A little bit of ash within that lignin really doesn't matter. So if we can integrate that a little bit better, I think there's lots of areas where lignin can be used in the future. And so just acknowledge over my group members that have worked on lignin over the years, and also thank for the Fin series for the kind invitation to speak this morning. Thank you.
Just you can, Scott, just stay there for a second. So thank you for sort of walking us through the really, a lot of the new scientific sort of advancements in lignin.
Yes.
Do you have a favorite? Is there something that makes you really excited about?
I would say potential, I would say there's a lot of, my favorite would be carbon-based materials, I think, right now.
Yep.
So, yeah.
Mine too.
Yeah.
Well, thank you, Scott.